Steve D'Antonio here in the engine room of this boat. Today I'm going to talk to you a little bit about running gear. Essentially we'll go over the whole system from end to end, from the output coupling on the transmission all the way to the nut on the end of the propeller shaft. Starting at the engine room side, we're looking at, in this case, a coupling, excuse me, and this coupling is actually part of a thrust bearing system. That is an optional component in running gear systems, but this boat does have one. Thrust bearings are actually very beneficial in that they separate the thrust from the propeller, or that is created by the propeller, from the engine and the engine's motor mounts, more importantly. So the engine can rest on softer, more resilient mounts because it's not absorbing thrust from the propeller as well. It is simply supporting the weight of the engine and absorbing vibration and torque from the engine, but not thrust. So the thrust bearing carries that thrust load, transmits it to the hull through flexible bushings, and it uses a coupling very much like the coupling that you would find on the transmission, which we'll look at in a minute. So from this coupling component right here, you can see there are coupling bolts and nuts that go all around that connect the propeller shaft coupling to the output coupling on the thrust bearing. This is where the alignment is done. So we talk about alignment in some of our other videos and articles that I've written, and how critically important propeller shaft to engine alignment is. This is really where the bulk of that work takes place, is measurements between the faces of these two couplings, the output coupling and the propeller shaft coupling. The importance of that proper alignment can't be overemphasized. Again, we have a video and several articles on that subject, but also the importance of the fasteners that are being used here, also highly important, as you can imagine, because this is the only connection between the engine's output and the propeller shaft. So these fasteners should be a grade 8 fastener, which is a high strength fastener, carbon steel, not stainless steel. The nuts need to have a locking mechanism. In this case, these nuts are a what's called a nylock nut. It has a nylon ring that is embedded in the end of the nut and acts as a locking mechanism so that these fasteners cannot loosen on their own. These should be installed with a torque wrench because the torque is critical, and that torque is a function of the grade of the fastener and the diameter of the fastener and the type of threads that are used. And so from that point heading aft, we have the propeller shaft here. In this case, this vessel has a dripless stuffing box. So there is a lip seal style stuffing box in this case, or a lip seal style seal. So there is a lip seal embedded in here underneath this cap, which is held in place with these fasteners. These two carriers hold spare seals in this case. So if the seal has to be replaced on this type of stuffing box, this ring is removed by taking these fasteners out. The seal is pried out of there and cut off the shaft. This carrier is separated by removing the screws on either end of it and freeing or exposing the new seal. That seal is then pressed into place and this cap put back on. The seal passes through this cap because it's flexible, pushed into its seat, and then this cap goes on to retain it. And again, in this case, there are two spare seal carriers to hold extra seals. If you didn't have spare seals for this type of stuffing box, you would have to separate the propeller shaft from the coupling. You could do that in the water if you had to. Move the shaft aft, put a new seal on, put the shaft back into the coupling, and then move it into the carrier on the stuffing box. That's a bit of work, and for that reason, many people opt to utilize this optional spare seal carrier, and sometimes you'll see 2 or 3 or 4 of these even on here, so that you never have to go through that trouble of separating the shaft just to change the seal. So always good to have those for this type of stuffing box once again. The other item that is noteworthy here is you can see this stuffing box has 2 water feeds on it. That is a system that is designed to be used on a twin screw vessel, so that if you are running on only one engine, that the stuffing box for the non-running engine is still being supplied with water for cooling and lubrication. So it essentially cross feeds water injection between the two stuffing boxes on both sides, so that regardless of which engine is not running, you'll have cooling and lubrication water being pumped into that stuffing box. Now, there's one caveat with that system that is very important to understand. For the non-running engine, if the stuffing box is being pressurized, it's possible that water could be pushed back up the hose that would normally be supplying water to that stuffing box, but is now idle, back up into the engine to the location wherever it is drawing or having raw water supplied. It's possible for that water to back up into the exhaust system and then back up into the engine, depending on the design of the exhaust system. So, if it is not a self-draining exhaust, meaning from the high point of the exhaust system inside the engine room to the discharge on the boat, if that is not a continuous downhill run, then it's possible that this feed water could fill up the exhaust system, and then that would overflow back into the engine. So if you have this type of arrangement, it's very important to understand how it works, and it's important to have an isolation valve at the engine where that raw water is being supplied to the stuffing box, so that if you are running on one engine, the non-running engine should have that isolation valve closed, so that water can't essentially run in the wrong direction back up into the engine. From there, you can see there's a flexible hose here. It's sort of bellows shaped in this case, and it's silicone that connects the stuffing box to what we call the shaft log. The shaft log is the tube or the pipe that travels outside or to the outside of the vessel. The shaft travels through it, and nothing actually touches that tube on the inside. The shaft is located in the center of that tube in that shaft log, centered and parallel with that tube. That is the means by which the shaft exits the vessel, essentially. The stuffing box's main hose, again, this large one that is sort of bellows shaped, connects the stuffing box to the shaft log. It's important that that hose be flexible, particularly for a stuffing box like this that has to float on the shaft and somewhat self-align. This stuffing box does have a bushing inside of it that is water lubricated, that helps this stuffing box align itself to the shaft and keep the seal properly aligned. In order for that to work properly, that hose has to be flexible and supple. Now, on a conventional stuffing box, that's less important because the packing material supports the stuffing box to some extent, whereas in a lip seal type arrangement here, that seal is a little bit more delicate and not capable of supporting the stuffing box on the shaft. So the flexible hose function is critical for a dripless type stuffing box, either this style or the alternative, which is a face style stuffing box, dripless stuffing box. In both of those cases, you need a flexible hose to allow those stuffing boxes to float. And that includes the water injection hoses. These two hoses, or even if it's only one on a single screw application, you'll notice these are both silicone and also very flexible, so that they're not side loading this stuffing box and preventing it from self-aligning. So again, critical that that stuffing boxes, particularly dripless stuffing boxes, or let's say only dripless stuffing boxes, are able to float freely on the shaft and not be restricted in any way and not be side loaded in any way. Now we're looking at the forward portion of the thrust bearing assembly. This particular thrust bearing uses what's called a constant velocity, or a CV joint. Those are familiar to many people because they're used on automobiles, on front-wheel drive automobiles in many cases. So there is a flexible joint in each half of this, or each one of these carriers, that is bathed in grease. There is a shaft between them, and there are boots that are flexible that keep the grease in and allow that constant velocity joint to move, so that there can be a misalignment between the output coupling on the engine and the input coupling on the thrust bearing. So one of the advantages to a thrust bearing system like this is, in addition to it being a thrust bearing and absorbing the thrust from the propeller, it also enables the engine to be installed at an angle that is different than the propeller shaft. Again, this assembly, this double CV joint assembly, allows the engine to be at a different angle. It's absorbing essentially that different angle between the propeller shaft and the engine. So definite advantages to that. The engine can be more level. Depending on the design of the vessel, it means the overhead of the engine room could be lower, and the overall height of the boat or freeboard for the hull could be lower, because that engine angle is more closer to level or even completely level, and that's possible with this CV joint assembly. Now, if you look further aft, you can see these bolts back here. Those are retaining the thrust bearing that is on the other side of this bulkhead. This is an aluminum vessel, so this is an aluminum bulkhead, but it could be steel in some cases, and it usually is on a fiberglass vessel. In some cases it's actually fiberglass, but again, here aluminum, because this is an aluminum vessel. These fasteners are securing the thrust bearing, and between this bulkhead and the thrust bearing on the other side are rubber bushings that again absorb that thrust when the engine is, or the transmission is in forward and all of this wants to be pushed forward. Those bushings absorb that thrust, and there's no movement from here forward, fore and aft, so that the engine is not being pushed forward, or the transmission and the engine are not being pushed forward by the thrust from the propeller. All of that thrust is being supported and stopped essentially here by this bulkhead and absorbed by the bushings that are on the other side of this bulkhead. With CV joints like this, one of the things to watch for is these boots can wear out, and you can end up getting leaks in these, and it'll start to leak grease. And when it does, because this is spinning, it'll sling this grease all around this area. You'll often see a line of grease if it's actually leaking. So these should be inspected regularly. There are also some very stringent requirements about the angle of these CV joints during the initial installation process. You don't want perfect alignment essentially with these. You want actually to be a slight misalignment, because that ensures that the CV joint actually has some movement in it, which spreads the grease around inside those CV joints. So those instructions need to be followed very carefully during the design and installation process of both the thrust bearing / CV joint assembly and the engine itself. So if this installation did not have a thrust bearing, then this output coupling on the transmission would be attached to a coupling that would be connected directly to the propeller shaft. In that case, this is where your alignment would take place. These two coupling halves would be separated, and a feeler gauge would be inserted in here to determine what the clearance was. All of the items that I pointed out earlier about fasteners hold true here as well. These are, or should be, grade 8 fasteners installed with a torque wrench and a locking mechanism, and they are carrying or supporting all of the torque load from the output of the engine, so they play a very important role. It has to be the strongest possible fastener that can be used in that application. Again, not a stainless fastener. That should be a conventional carbon steel fastener that is ideally a grade 8. Looking at the essentially the other half of the running gear, the part that's on the outside of the boat, obviously this is the propeller. Looking at prop nuts here, you'll notice that these are installed, the larger nut is installed last, what's called the full height nut. The half height nut is up against the propeller. That's actually the correct orientation for the nuts. That's dictated by ABYC, Society of Automotive Engineers, the Navy, the Coast Guard. A variety of institutions are very clear about that the half height nut goes on first, and the full height nut goes on after that. We do have an article on that subject which we'll include in this video, a link to it in this video that talks about propeller installation specifically, gives more details about that, including the nuts themselves. Notice that this prop has threaded holes in the aft-facing side of the hub. This one actually has a set of 3 holes that are here. Those are designed to be used with a propeller removal tool. That's an ideal arrangement, and I would encourage you to have, if you're buying a new propeller, if you're having a propeller worked on, include having those threaded holes drilled and tapped into the hub of the prop so that you can use a propeller removal tool. Or even if you're not removing the prop yourself, if you find yourself someplace where the prop has to be removed, having that tool available for whoever's doing that work could be very handy. It's low impact, meaning it doesn't harm the propeller or the shaft or transmission in the removal process, so highly desirable. Again, if you don't have those holes on your prop, the next time it's off you can have them added, or if you're buying a new prop, those are really critical to have. You'll see that there's a cotter pin in the end of this shaft as well that's bent over like this. That is really designed to simply prevent these nuts from falling off if they happen to loosen. Hopefully that never happens. If the nuts loosen and the prop separates from the taper on the shaft, you'll probably know about it because it's going to shear the key, and the boat is not going to move anymore because the shaft will spin independently of the prop, but at least you won't lose the whole propeller arrangement. Now, one of the tests that I do to determine if the shaft alignment with the shaft bearing, which I'll talk more about in a minute, is correct, is to turn the prop by hand like this. If I can turn it with relative ease, while this isn't scientific, it does tell me that the alignment is probably fairly good. Again, that's the alignment between the shaft and the bearing, not necessarily the alignment between the shaft and the engine, but the alignment between the shaft and the shaft bearing, or sometimes called the cutlass bearing. If that is good or relatively close to what it should be, then I can turn this fairly with ease. Now, if this were wet, meaning this boat had just been hauled out of the water, I could turn this and it would move a little bit when I let go of it. And even this one being dry, it does move a little bit after my hands separate from the prop, as you can see. If I do that and it stops dead the moment my hands come off of it, chances are there's an alignment issue. Again, this one's dry, but when it's wet, if you do that, you should get a little bit of movement in the prop after you let go of it. If you don't, chances are either there's an alignment issue between the shaft and the bearing, or the bearing could be swollen. That's not an uncommon issue where the material that is used in the bearing is a rubber-like material. If that absorbs water and it expands or swells, it can capture the shaft and make it very difficult to turn this. And certainly when you do the spin test like that, it won't move at all once you let go of it because there's so much resistance between the shaft and the bearing. If you look at the leading end of the propeller hub in this case, you can see some deformation. It's a little bit mushroom shaped. It's kind of tilts up right here. That's visible all the way around this hub from where I can see it anyway. That's an indication that somebody's been hitting on this hub with a sledgehammer to try to remove the prop from the shaft. That's an undesirable way, let's say, of trying to separate a propeller from a shaft. The connection between the propeller and the shaft is what's called a tapered hub. It's cone-shaped. The propeller shaft is cone-shaped, and then the hole in the hub of the propeller is equally cone-shaped, and the two fit together very tightly, ideally, and are very hard to separate. They should be very difficult to separate. But trying to separate those using blunt force, like with a sledgehammer, is again undesirable because that shock load is being transmitted up the propeller shaft to the transmission, and the bearings in the transmission are really taking a beating when you do that. A better way to remove a prop is, as I mentioned earlier, using the threaded holes in the aft end of the hub and a puller that simply exerts force between the end of the propeller shaft and the propeller hub There's no shock loading, no sledgehammer being used typically, maybe just a little bit to shock it once and release the tapers from each other, but you're not beating on the propeller to separate it from the shaft. So again, this is an indication that this prop was removed in a way that really is less than ideal and should not be done. A proper propeller puller should be used to separate the prop from the shaft. This arrangement is also set up with a line cutter or a line and weed cutter. That's this device right here. These really come in two formats. This style, which uses just the cutter itself, the blade, that this is a serrated blade, and these are quite sharp. And as the line wraps around the shaft, the tension increases on these teeth and it eventually cuts through it. There is another style that uses a rotor and a stator, essentially a two-part cutter, where it is more like a guillotine that is slicing the line. Either way, it's a good idea to have something here so that if you run over a line, you have some chance of at least being cut out before it really wraps itself up tightly and does some kind of damage to this setup here. This is the propeller shaft here. The distance between the trailing end of the shaft bearing, this right here, and the leading edge of the prop hub should be ideally no more than the equivalent of one shaft diameter. So if this shaft is this diameter, it should be no more than that. This looks like it's pretty much equal to me. I'm not using a ruler, obviously. But you don't want too much overhang because you start to get some wobble and you could potentially fracture the shaft like that. So ideally no more than one. On a slow boat, a full displacement boat, you could go up to 1.5 shaft diameters, but again, ideally one shaft diameter of overhang is the goal. Here, as I pointed to this just a minute ago, is the trailing face of the shaft bearing or cutlass bearing. The shell of that bearing is usually made out of brass. In some cases it could be a phenolic or a non-metallic material, especially if you're inserting it into a shaft log on an aluminum vessel. Then you would not want to use brass because those two metals are incompatible. On a fiberglass vessel, this tube, again, this is the shaft log, goes up through the keel on this boat and comes out on the inside. That's where the stuffing box is attached. The shaft bearing fits into the inside of that tube with a interference fit, a press fit. It goes in lightly and then uses set screws. There's a hole here and another one on this side that have set screws that go in and secure that bearing to keep it from coming out and to prevent it from spinning. When those screws are installed, or before they're installed, I should say, the shell of that bearing needs to be slightly drilled so that there's an indentation or a dimple in it into which that set screw fits. The face of the set screw should have a matching angle as the drill that is drilling the indentation so that those two match up nicely. When you're doing that, you have to be careful not to drill completely through the shell because you don't want that set screw to go through the shell and begin to exert pressure on the inner bearing, which is again a rubber-like or flexible material. So a slight indentation in that shell and the set screw fits into that indentation tightly and prevents that bearing from moving. Running gear on this vessel is exposed, so unlike the previous vessel that was a shaft lug that traveled through the keel of the vessel, didn't have a strut. This vessel has a strut. This is what's called a V-strut because it uses two sections that are V-shaped. This supports the shaft. We have a shaft bearing inside of here, cutlass bearing inside of this that is pressed into this V-strut and retained again with set screws, just like the other one is, 4 in this case. Propeller shaft travels up and into the bottom of the vessel, traveling through the shaft log, and so you can see the shaft log. It's a tube here that comes out of the bottom of the hull, and there's another bearing in here, another shaft bearing. So when you're talking about shaft alignment as opposed to engine alignment, it is the alignment of the shaft with these bearings, this bearing and the bearing down there. Usually a laser is used to align those two. That alignment process is somewhat complex and requires special skills to do. We'll include a link in this video that talks more about shaft alignment and how that's done. But when you have, particularly when you have more than one shaft bearing like this does, then that alignment process becomes a little bit trickier and again requires some special knowledge to understand how to do that. The adjustment is made by shimming the strut again, so that takes some special skills and experience to do that properly. But in this case, shaft log, again, bearing inside there, propeller shaft. This exposed portion of the propeller shaft is visible, as you can see, obviously, and in this case it's been coated with a zinc-based anti-fouling material. That's a good idea for running gear, to use something to prevent anti-fouling, especially when you have this much exposed shaft. If you have hard barnacles growing on this, it creates turbulence that gets drawn into the vacuum side of the propeller blades and can create vibration and inefficiency. So keeping this portion of the shaft clean is important. Hi, Steve D'Antonio here in another of our technical instructional videos. Here at Deltaville Boatyard, they've been nice enough to make their facilities available to us to produce these presentations.